Okay, so good evening everyone and welcome to the sixth session of the course Dynamical System and Control. So today we'll be mainly looking at type of equilibrium point what we have discussed for the linear system. Today we'll see it for the non-linear system. How can we conclude about it using linearization or some other taking technique. Or at last we'll see some notion of Lyapunov stability and we'll see how to check that. Okay. Okay, so let's begin this session. So, okay, so let us set up what the problem we are addressing. So consider this system. This is a linear system, non-linear system with where the non-linearity is given by P and Q. Okay. So over here we have the assumption that 0, 0 is an equilibrium point. Okay. And we have to check whether this, so let me recall first what we have seen in the last class. So we saw these kind of notions that suppose you have x naught y naught as an equilibrium point, right? So we classified it into four types, right? So one was a spiral, then we have seen center, then we had saddle point, okay, and then we had the notion of node, right? So we defined what these points are, and for the linear system we even characterized it using the eigenvalues of the linear system. So today, looking at the linear part, okay, so looking at this linear part, okay, or the linearized part, we'll see here we are considering the 0, 0 equilibrium point. So over here, okay, so I mean I should not say just the linear part, so it's kind of it's linearized system. Okay, so I should not write this, maybe the linearized system, linearized system about the point 0, 0. Okay, so looking at whether the equilibrium point 0, 0 is a node, saddle point, center of or spiral of this system, can we conclude about the nonlinear system? So this would be our question that we would like to address. Okay, so let's see how we can deal with that. So these are certain assumptions that we made. So you remember, like, we also studied stability, like whether the equilibrium point is asymptotic stable or unstable. So for that, when we talked about stability of nonlinear system, so we used the linearization, and looking at the stability of equilibrium point for the linearized system, we concluded something for the nonlinear system, right? And we had similar kind of assumptions over there. So we had that this matrix or the linearized system should have so this is nothing but it's another way of saying that 0, 0 is the only equilibrium point of the linearized system, right? This is what this condition means, right? Because if we had this matrix y prime equal to ay, where a is nothing but a b c d, this matrix, right? So this equilibrium point means that ay should be equal to 0, right? Now since this is nothing but saying that determinant of a is non-zero, so when determinant of a is non-zero, this will have trivial solution, which is y is equal to 0. So the only equilibrium point for this linearized system is 0, correct? So this is what this assumption is saying, the first assumption. The second assumption is that at 0, 0 p and q should vanish. Why? Because this 0, 0 is an equilibrium point for the nonlinear system. This is what we are looking at. Okay, so in the assumption we had 0, 0 is equilibrium point. Okay, so that this is what this means, correct? So this is another condition. And the third condition is that these limits, so here norm means Euclidean norm, so this is nothing but x square plus y square. Okay, so this limit should exist and both limits should be equal to 0. Okay, so these conditions or assumptions what we are looking here, we saw in the case of when we were trying to study the stability of the nonlinear system. So similar assumptions were there as well. Okay, so under these assumptions, these are the results what we have seen for the stability, right? So the nonlinear system, so for this, okay, so here we are talking about zero equilibrium point. So this, where we said that this is asymptotic stable for the nonlinear system if it is asymptotic stable for the linear system, right? And equivalently saying that the eigenvalues of A should have negative real part, right? This is an equivalent criteria for the asymptotic stability. Okay, so this is what I'm just recalling it because we'll see this here as well. Okay, we'll see some problems related to these things. The second thing what we saw, that it was unstable if the linearized system, the equilibrium point 0 0 is unstable for the linearized system, right? So in these two conditions we saw that using the stability of the linearized system we concluded about the nonlinear system. And when the equilibrium, the eigenvalues of the matrix corresponding to the linear system had real part equal to 0, so this is what has been written, at least one eigenvalue has 0 real part, in that case we could not conclude, right? We saw some cases, in some cases it was becoming stable, in other cases it was not, right? So we cannot conclude when the real part is 0. So this is what we saw earlier. In a similar way we'll see that how to characterize these equilibrium point as in these four categories using the linearized idea, I mean linearized result. Okay, so what we have seen so far, when, okay, so maybe you can consider these three cases together. So what we saw, that when the eigenvalues are real, okay, real and of same sign, okay, then in these cases we saw that the 0 0 is node, correct? When it was real and at opposite sign, then we saw that it is a saddle point, right? So let me first tell you about these things. So suppose that you have a real eigenvalues of the linearized system, of the linear matrix, okay, so, and they have, so if they are unequal and of same sign, then from this case we know that the linear system, the equilibrium point is a node. But for the nonlinear system also you can say that the equilibrium point is a node. Okay, so nothing changes in this case, even if when you have a real and equal eigenvalue but it is not diagonalizable. That means it has, so when we are in 2 cross 2 matrix, so not diagonalizable means the algebraic multiplicity and geometric multiplicity are not the same, right? In that case only we have this non-diagonalizable thing. Then in that case also it is node for the nonlinear system. But if they are real, equal and diagonalizable, okay, in that case the nonlinear system, okay, it can be, the equilibrium point can be node or it can be spiral. So we cannot conclude, so we know that the linear system, for the linear system 0 0 is a node, but for the nonlinear system we cannot conclude in this case when they are real, equal and diagonalizable. Okay, so this is one case where the difference arises, right? This is the one case. Okay, now moving forward, so when this eigenvalues are real, unequal but of opposite sign, then we know that for the linear system it is a saddle point, the equilibrium point 0 0 is a saddle point. The same can be said for the nonlinear system. Okay, so this is same in this case, we don't have any difference over here, saddle point remains preserved. Okay, for the nonlinear system also it will be a saddle point. Okay, now coming to the complex eigenvalues. Okay, so this is kind of a similar to what we have seen in the case of a stability. Okay, so see, when you have the real part is non-zero, in that case the equilibrium point is a spiral for linear as well as for non-linear. Okay, so here I have missed it, for linear and non-linear both. Okay, so nothing changes here also. The spiral, if it is the equilibrium point is spiral for the linear system, then for the non-linear system also it is a spiral when the eigenvalues have non-zero real part. But just like in the case of a stability, when the real part is 0 we cannot conclude. Okay, so for the linear system we know that it is a center, right? When you have circle kind of thing, but for the nonlinear system it can be center or a spiral. Okay, so this case, similar to what we have seen for the stability, is true for here also. Like there is some distinction between uh, the result. Like it is a center for the linear system, but for the nonlinear system it can be center or a spiral. Okay, so this is the whole characterization for the nonlinear system. Okay. Okay, so let us see one example related to that. Okay, so we have to talk about this, the type of equilibrium point. Okay, so the critical point and equilibrium point are the same thing, so we have to characterize it where what kind of equilibrium point 0 0 is. Okay, so let us look at the linearized system. Okay, so in this case the linearized system would be just this. Okay, so I hope you know what so I should have told you earlier, but linearized system is like df, the derivative at that point, whatever point you want to evaluate. Okay, so here you can see, so let me say this is your f, right? So just 2x minus 3y plus 4x square plus 2xy. Okay, now what is the Jacobian matrix corresponding to this function? Right? So this function f is a function from R2 to R2. So the derivative is a linear operator, right? And it's map from R2 to R2. Okay, and here you have a matrix basically. So df, if you want to calculate, so let me write it here. So df of xy, if you want to write it, so it's like the so let me say this is your f, this is your g. Okay, so you have del f by del x, del f by del y, del g by del x, and del g by del y. Okay, so this is the Jacobian matrix. So the linearized system is given by y prime equal to df, okay, at that equilibrium point. So it's called linearization, or what we say is system linearized around the equilibrium point 0 comma 0. Okay, this is what we say. So it is given by y prime equal to df 0 comma 0 y, right? Okay, so here, here I think I wrote it something wrong. So df is a map from R2 to this R2, and it is represented as a matrix. So this is a linear operator, so you can represent it as a matrix. Okay, so I'm not going in this detail. So over here we know that df 0 0 is this one. So let me calculate this. This is nothing but, you see here you get 2 and then plus 8x, here you get minus 3 plus 2x, and here you got 1 and minus 3y plus 12x square, and then here you differentiate, you get 2 minus 3x. That's it. So now if you substitute x equal to y equal to 0, what you get is 2 minus 3 1 2, right? So this is nothing but this corresponding, so this is the corresponding system, right? Okay, so this is how we linearize it. Okay, but in 0 0 case, almost every time like we get this kind of matrix. So that's why most of the places I think this has been written in the lectures or in the slides what you have seen. Okay, so that's it. So this is how linearized system looks. So let us look at the equilibrium point, what kind of equilibrium point it is for the linear system. Okay, so the system what we have got is, so linearized linear system. So y prime equal to, this is 2 minus 3 1 2 y. Okay, Now look at the eigenvalues for this matrix. So let us say that this is a matrix A. Now A minus lambda I equated to 0. So what we have is 2 minus lambda minus 3, 1, 2 minus lambda equal to 0. So lambda minus 2 whole square, sorry, plus 3 equal to 0. So you have lambda square minus 4 lambda plus 7 plus minus 16 minus 28 by 2. So this is nothing but 2 plus minus, you have here 12, so root 3, so root 3i, correct. So this is what you get as the eigenvalues, right? So okay, that's fine, but let us look at the assumption. Like, we have to verify all these properties first, then only we can use this result what I have stated here. So these things are true, these all 6 points are true under these assumptions. Okay, so let us check the assumptions also, then we can conclude. So the first assumption was that this matrix should have non-zero determinant, right? So you can clearly see that determinant of A is nothing but 4 plus 3, which is 7, and this is non-zero, right? The second assumption was that, okay, so what was this? So P and Q, let us write what P and Q are. So P of xy, if you see, this is 4x square plus 2xy, right? And qxy is minus 3xy plus 4x cube. So these are the non-linear part that we have. Okay, so you can clearly see, so this is my, let me write it somewhere else. Okay, so the first thing, it's clear that P 0, 0 and Q 0, 0 is 0, right? It's obvious from the expression. The third thing was that to verify this limit xy tending to 0, 0 for this 4x square plus 2xy upon root x square plus y square is 0, right? And in fact this is true, right? Everyone agrees with this fact. Is this fine, this point? These points are fine. Like, if you have doubts, you can ask if this is not clear. This and this. Okay. Okay, since no one is asking, I assume that this is fine with you. So all these assumptions are true. So looking at the linear system, we can conclude about the nonlinear system, right? Because all the assumptions are true. So here you can see that the real part of this eigenvalues lambda I, okay, by lambda I mean, so this is, let's say lambda 1 equal to 2 plus root 3i, and lambda 2 is 2 minus root 3i. Okay, so this real part is 2, which is positive, right? Then what do you know? You know that this is a spiral, where there, this one, right? So you know that this 0, 0 point is a spiral for the linear as well as for the non-linear system, right? So from here you can conclude, so this implies that 0 comma 0 is a spiral. Okay, spiral for the linear and nonlinear system. Okay, and you know that this real part is positive. Okay, that means it's unstable. I mean the spiral is unstable, right? So it's like, so suppose you are here, so for the linear part we know that the figure would be something like this, right? This kind of figure we will obtain if the solution starts, let's say here, then it will go away from the origin, right? Unstable, this is what it means, correct? And even for the non-linear system it would be like this, but maybe some like this kind of thing, not properly in this way, but some using, what do you say, some deformed picture of this one. Okay, so in this case, like when you have instability, so you can see that this origin can be said that it is a source. Okay, so in last session I think I mentioned it. So when you have instability kind of thing, you have source, and if the arrow is reversed, okay, if this kind of thing is there in the picture, right, so then it will go spiral and spiral. So in that case it's called sink, that it is going sinking to the origin. Okay, so these are two things. Okay, so these are concerning the stability. So as of now, what the question was, the question was to identify the type. Okay, and by the type I mean whether the equilibrium point is node, spiral, center, or saddle point. Okay, but if you want to go for the study of stability, you can say that since the real part is positive, you know that it is unstable. Okay, so overall you can say that.
And here,
Yeah.
shall in this, whether we need to check the determinant if eigenvalue is real part is not zero,
Hmm.
then with the lambda with eigenvalue itself, we can tell that it is a spiral, right? Whether we need to do the second condition determinant of A
Oh,
and
this one you are saying?
whether, yeah, whether that is required.
I mean, if you are anyway, I mean this is kind of thing what I mentioned, just to look at the assumptions. Otherwise, when you find the eigenvalue, you know that the eigenvalues are non-zero. That means determinant is non-zero. That's true because
So,
determinant is just product of eigenvalues.
no, my question is whether we need to check the P of xy and Q of xy also, whether we need to check if eigenvalues. Initially, you have shown that conditions, right? For,
Correct, correct.
if any of that in that only two conditions, if it is not meeting, we have to check this condition, or always we need to check this P of x and Q of x condition.
You mean these two conditions? That's B and C part?
Yeah, right side. Yeah, right side at A, B, C.
So see,
Whether that we need to check for all conditions.
actually, I'll in a second I'll state one more theorem which is much more simpler. But over here, see why I made it to. I mean, I wrote this because this is something that is required to make sense of the question what we are asking. Because see, here if you look at the problem, I wrote that 0 0 is equilibrium point of the above system, right? That means this should be 0, right? The right hand side should be 0. So the moment I say that this is non-zero, that means anyway, uh, what should I say? So just to make sense that okay, 0 0 is the equilibrium point, these two conditions are put. So when you are considering the problem, it is automatic in some sense, right? When you are looking, so when you will be given a question, okay, then suppose you have been asked that whether 0 0 is equilibrium point or not. This is the first thing that you should look at in the question. If it is mentioned that for, I mean, determine the type of the equilibrium point 0 0, then it's fine that you know that 0 0 is equilibrium point. But when it's not given, you need to find it, I mean determine whether 0 0 is equilibrium point or not. In this case, like this is something, I mean it's not, it's obvious, these condition at least, and this also, like this not, but when you're dealing with these theorems here, we see in each of these points we have not talked about when the eigenvalue is 0, right? Because that case does not arises when we assume this thing, right? So
Okay.
So these are something which is just to make sense of the things, that's it. Okay, I mean, this is something that will come if you want to study this kind of thing. Okay, so this was the thing, whatever, I mean, all these points what I've written here can be condensed in this form. Okay, so before that, let me tell you one definition of almost linear system. Okay, so a non-linear system is called almost linear at the equilibrium points x naught comma y naught. Okay, if the linearization has isolated equilibrium point at 0 0. Okay, so it's like, suppose you have given y prime equal to fy, this is your non-linear system, and you know that this x naught comma y naught, or this y naught, is an equilibrium point, let's say. Then this system is called almost linear at this equilibrium point if the linearization, if you do y prime equal to df at y naught, right, this linearization system, if you consider like 0, okay, 0 should be equilibrium point for this linear, I mean linear system, and that should be isolated. So that is the main part, it should be isolated. Okay, so this, now this theorem whatever I'll say, so far we have dealt with just 0 equilibrium point, like all the theorem what I have mentioned is about 0 0, right? So this is when you want to deal with any other critical point which is non-zero, this is best, and this is written in a very condensed form. In the case you don't have to deal case by case, but it has been written in a very nice way. So suppose that the system what you are dealing with is almost linear at that equilibrium point. Okay, and this statement is nothing like you have to check determinant is non-zero, and that's enough. Okay, if you have determinant is non-zero, that means 0 0 is the only equilibrium point. Okay, and that means in the neighborhood you cannot find any other in neighborhood, what, not any other point can be an equilibrium point, right? Okay, so I mean determinant is much more condition what you are asking, but here you just need isolated means like if you look at 0 0 in a neighborhood, you should not get any other equilibrium point, right? So df y naught, this matrix, okay, should vanish. I mean if you apply, so let me read, so let me call this matrix as A. Okay, then ay equal to 0. Okay, this is possible. Suppose you know that a at 0 is 0, that is obvious, right? But ay 0, it should not occur, so there should exist a neighborhood around 0 0 where this ay should not be 0. Okay, that's what this isolated means. Isolated means in the neighborhood there should exist a neighborhood where there is no other critical point other than origin. Okay, okay, so if this condition is satisfied, we say that the system is almost linear, and for that system we have this theorem. Now suppose you have two eigenvalues, okay, of the linearization. Okay, so the linearized system. Okay, then this critical point P, okay, so this critical point P is for the nonlinear system. I hope, okay, it's not written, but this critical point means for the nonlinear system, for nonlinear system is of identical type to the type of equilibrium point 0 0 for the linearized system, except these two cases. Okay, so suppose you have been given a nonlinear system, you just linearize it around that point, around that equilibrium point, and now just look at what the type of 0 0 equilibrium point is for this system, for the linear system. Okay, except these two cases, that means when the eigenvalues are equal or when they are purely imaginary. Okay, in this case we know, like here we had much more, so you see here also they are real and equal, but if it's non-diagonalizable we can conclude about the nonlinear system, but in this theorem that part is not there. Okay, so we just, if the eigenvalues are equal or they are purely imaginary, then in that case we cannot say anything, but other than that we can conclude. Okay, the type would be same. Okay, okay, so I'll discuss few examples based on that. So look at this system. Now for the first task would be To find the, here in the question you have been asked that you have to find all the critical points, and at each critical point you have to say what is the type of that critical point. Okay, so let us first determine the critical point. Okay, so that means this should be 0, so x minus y minus x square plus xy equal to 0. The second is minus x square minus y equal to 0, right? So this implies x minus y minus x, if you take common you get x minus y. This means x minus y, okay, and from here you get y equal to minus x square. Okay, let me see, this is 1 2, so from 1 you have this x is equal to y or x is equal to 1, right? So in this case from 2 what you can obtain is y equals minus y square, right? And from here you obtain, so using 2, so from here you obtained y is equal to minus 1, right? And here, so from here y plus y square equals 0, that would mean y 1 plus y equal to 0. This means y is 0 or y equals minus 1. So overall the critical points what we have is the following. The first point is this, what do you say, this is 1, so y, okay, so from here also I have to find what x is, so this would mean, so x is also equal to y, right? Because of this condition, sorry, so we had this condition in our mind, so this would imply 0 0 is an equilibrium point. Corresponding to this we have minus 1 comma minus 1 as equilibrium point, and corresponding to this we have 1 comma minus 1, right? So we have 3 equilibrium points for the nonlinear system. Now we'll see the linearization around each of the point. Okay, so now, sorry, so let us look at the linearized system. Okay, so for linearization let us look at the Jacobian matrix, so df x comma y. Okay, so let me write it capital. Okay, so what was my f and g? So you have x minus y minus x square plus xy minus x square minus y, right? So let me just, okay, so this is nothing but you have 1 minus 2x plus y, and then you have minus 1 plus x. Here you have minus 2x minus 1. Okay, so this is the Jacobian matrix. So let us consider this, so I'll call this case maybe A, B and C. Okay, so in this case the linearized system is y prime is equal to df 0 0 y, and this is nothing but y prime equal to, so this is 1 minus 1 0 minus 1, right? In the B part we have y prime equal to df minus 1 y, this is y prime equal to, so you substitute minus 1, so what you get is, so here you will get 2, here you will get minus 2, here you will get 2 minus 1. Okay, and the third case would be y prime equal to df 1 comma minus 1 y, that is df 1 comma minus 1 would be, so you just substitute x equal to 1 and y as minus 1, so 1 comma minus 1, so this is minus 2, this is 0, we'll have minus 2 then minus 1. I hope everything is correct. So minus 2 0 minus 2 minus 1. Just check if something is wrong. Okay, so this is the system, and you see, according to the theorem what I mentioned, you just need to check whether 0 is isolated critical point or not, right? So you can clearly see over here, so all this matrix here, if you see this determinant, okay, so I think I should have written y. Okay, so the determinant of this matrix, okay, so let me say this is AA, AB, this is AC. So determinant is non-zero, right? Over here, this is minus 1, which is non-zero. Here also, if you see determinant of AB, if you see this is minus 2 and then plus 4, which is non-zero. Here also determinant of AC is equal to 2, which is non-zero. So in all the cases, 0 0 is the only equilibrium point. So there is no question of isolated or something else. Like the only equilibrium point is 0 0. Okay, so we are in the setup. Okay, sorry, this one. So we know that all the linearized system is, or the non-linear system is almost linear around that point. Okay, so at each of the critical point, then now we just need to look at the eigenvalues, what eigenvalues we are getting. Okay, okay, so over here 1 minus, let me see, a minus lambda I equal to 0, 1 minus lambda minus 1 0 minus 1 minus lambda. If I solve, I get lambda minus 1, lambda plus 1, and then equal to 0. Then from here what we get is lambda is minus 1 comma 1, right? Okay, so we, from here what we can conclude is, what would be the conclusion? Here the eigenvalues are real and of opposite sign, right? So that means the equilibrium point, so the equilibrium point 0 0 for the linear system is saddle point, right? And same for the nonlinear system. So 0 0, so from here what we can conclude is 0 0 is saddle point for linear and nonlinear. Okay, so both systems. Okay, now let's look at the eigenvalues for this system. If I do, what I get is 2 minus lambda minus 2, 2 minus 1 minus lambda. So here you see this is lambda plus 1, and then lambda minus 2 plus 4 equal to 0. So lambda square, then you have plus lambda minus lambda minus 2 plus 4, which is plus 2. Okay, so from here what we get is lambda is, so you get 1 plus minus b square minus 8 by 2. So over here also you see this is imaginary part, this is complex part. So the real part over here, we see that the real part is non-zero, right? So again, so here also 0 0. So you see here the point would be like this. So 0 0 is spiral for the linear system. right? And what was the point we were considering? Minus 1 comma minus 1. So minus 1 comma minus 1 is spiral, right? It would be preserved because they are not equal and they are neither purely imaginary, right? This is spiral for non-linear system. Okay, so this is what we can conclude for this system. In the C part, if you do this a minus lambda equal to 0, this would mean 1 plus lambda, 2 plus lambda equal to 0. So here you have lambda equal to minus 1 and minus 2. Again, here the eigenvalues are real and distinct and of the same sign, right? So in this case, what we can conclude is 0 0 is node, and in fact here you have a stable node, right? So 0 0 is node for the linear system, and this point, so we have linearized around 1 comma minus 1. So this 1 comma minus 1 is node for the nonlinear system. Okay, so this is what, using this theorem, we can conclude for the non-zero critical points. Okay, except these two critical cases. I mean, here we cannot say anything, but other than that, we have this theorem. Okay. Okay. So let us look at some more example. So here you see you don't need to, I mean, in this theorem there is nothing has been mentioned about those condition, that the, because here anyway we don't have p and q, we have just this kind of system, y prime equal to fy. Okay, so we don't have any such conditions what you were asking about in this case, right? We just have this kind of similar to this one, which is in terms of almost linear system. I mean, this condition, where is it, almost linear, right? Which tries to make sure that the linearized system what we get has 0 0 as the critical isolated critical point. Okay. Okay, so let us see for more examples. Okay, so let us look at this one very quickly. So over here you can see that, maybe I'll not write the details. So here also you see the linearized system. Okay, so the linearized system would be nothing but just this part. Okay, because you see you have this polynomial kind of thing. Now whenever you differentiate with respect to x or with respect to y, you will have some x raised power k, y raised power, I mean, km, right? This kind of thing. So whenever you put 0 0, this will vanish. Okay, so the only thing what will be remain while taking the Jacobian would be this part. Okay, so the linearized system would be y prime equals 0 minus 1 1 0, right? This would be the this system. Okay. Okay, so now you see here the eigenvalues are, if you try to calculate this, say this is a, then a minus lambda I equal to 0 if I do, minus lambda minus 1 1 minus lambda, so you have lambda square plus 1 equal to 0. So here you get lambda is plus minus iota. Okay, so what can you say something about this? Here see the real part is 0, right? So we cannot conclude. So here what we can say is that 0 0 is a center for the linear system, and 0 0 is either center or spiral for the non-linear system. Right, we cannot conclude anything more than this. Okay, so here we'll try to deal it independently. Okay, so see, this is the system what you have. Now you can look here that if you multiply this by x and this by y, you see, and you add them up, so you, I'm saying x prime plus y prime, if you do this and this will cancel out, so here you will get minus xy and here you will get xy, so these two will add up to 0. Okay, so you will lose these two terms, and here you have x raised to the power 4 plus x square y square, here you have y raised to the power 4 and again x square y square, so you have 2 here, so that means it's nothing but x square plus y square whole raised to the power 2, right? Okay, so you have this. So you have this condition, and from here what you can conclude is d dt of 1 by 2 x square plus y square is x square plus y square whole square. Okay, so you can throw 2 here, so this is what you get, the formulation. Okay, and I think I discussed this problem earlier as well, I think in fourth session. Okay, when we were dealing with stability, and there I did a mistake, although I corrected in the PDF file, if you must have checked it. So that time I was saying that this is greater than 0, I mean something like this, then it is an increasing function, so it will go to, I mean, infinity, it wouldn't be unstable, this kind of thing I said. But in fact, if you solve this differential equation, okay, so what you can do here, you can rewrite this as d of x square plus y square upon x square plus y square whole square, and this is equal to 2 dt. Right, now if you integrate both sides, what you get is minus 1 by x square plus y square, and here you get 2t and then plus c. Okay, now if you put c equal to 0, I mean t equal to 0, from here what you get is c is minus 1 by x square 0, so here it's x square t y square t, so you will get x square 0 y square 0, this is the value of c. Okay, so from here what you can say is this x square t plus y square t is nothing but minus 1 by 2t plus c, where c is this quantity, so c is minus of x square 0 plus y square 0 whole inverse. Right, this is the thing what you get. Okay, so this is the explicit solution. Okay, I don't know whether you checked that file or not, but this is what we can say. So for all t maybe greater than 0. Okay, so this is what we get here. Okay, and note that when here I'll just mention, so here when we were talking about this stability around the 0 point, so the definition says that you start in a certain neighborhood of this 0, then the solution must exist in that neighborhood for any initial data taken in sum, so this kind of thing. So for any epsilon you choose the initial data. Okay, there should, I mean sorry, for any epsilon, so let's say this is epsilon, there should exist a small neighborhood delta. Okay, delta neighborhood, so that if you choose any initial point from here, the solution should exist in this, I mean should restrict itself to this epsilon ball, this, so that's why the initial data what we consider is non-zero, so this is always non-zero. Right, okay, so I mean that is, so this inverse makes sense, that's all what I meant to. So here, so this makes sense since x square, since x0 or as x0 comma y0 is non-zero. Okay, so this constant is meaningful. Okay, so this is what we can say. Now see the here, what does this mean? If you look at this expression, this x square plus y square is nothing but telling you that the I mean, if you write it in terms of polar coordinate, this is telling you the radius from the origin, right? So if x t y t is the solution, it's saying that how this radius or distance, how is it behaving, right? This is what this expression of x square plus y square tells you. Now as t goes to infinity, you can clearly see this is going to 0, right? So it's like the radius is decreasing, or am I saying the reverse thing? Just a second. So it's clear that it is a function of t, and as t goes to infinity, this ratio will converge to 0, right? So it's like the radius is decreasing and it's going to 0. So here we can say that it is a spiral, right? This is what we can conclude looking at this expression of x square plus y square. Okay, so we can now conclude. So from the theorem we say that it can be either center or a spiral. That's all we have concluded using the theorem. But getting this expression of x square plus y square, what we can say is, maybe leave it here. So from here, looking at the expression, what we can say is this 0 comma 0 is a spiral, and in fact it is a stable, right? So it's a spiral for, so you can say that it is a sink. Okay, spiral for the nonlinear system. Okay, now let us look at this one. So again, I will be a bit quick here. You can see that the linear system is this one, and it's in fact the same as this one. You see minus y x, here also this is minus y x. Okay, so here the 0 0 is a center for the, let me write the eigenvalues. Corresponding to linear system is plus minus iota, right? So 0 0 is center for the linear system, but and 0 0 is either center or spiral for the nonlinear system. Okay, so now using the same argument what we did in the last case, if we do x prime plus y prime, you see this will cancel with this and this will cancel with this, right? Here you will get x square y with minus sign, here you will get plus x square y. Okay, so what you got is this is 0, and this means that d dt of x square plus y square is 0. This means that x square t plus y square t is constant, and this is nothing but x square 0 plus y square 0, right? Right, this is what you get. Okay, so this means, what does this mean? That 0 0 is a center for the nonlinear system. Okay, so in these two examples you can see that the linear system has the same behavior, that the equilibrium point is a center, but for the nonlinear system in this case is a spiral, while in this case you get a center. Okay. Okay, so now let us look at this theorem called Poincare-Bendiction theorem. So what this theorem says, that suppose you have a solution xt. So I hope all these things were clear what I have said so far. Okay. Okay, then now let's talk about this theorem. So suppose you have a solution xt yt, okay, which is confined to some bounded region. Okay, that means that as t goes to infinity, it is remaining in some bounded domain. Okay, so this solution of this system remains bounded in the plane. Okay, we are in 2 cross 2 system, so that's R2, which is a plane, and that region does not contain any equilibrium point. Okay, so where the solution is bounded should not contain any equilibrium point. In that case, it says that its orbit, okay, must spiral into a simple closed curve. Okay, what does it mean? That so suppose you have this domain R, and you know that any solution, if you take that this, okay, not any solution, but suppose any particular kind of solution, this xt comma yt, you know that it is, as t goes to infinity, it is in this bounded region. Okay, and what it says, that you take any other solution. Okay, so this is the assumption what we have, and the one assumption is that this region does not contain any equilibrium point, does not contain any equilibrium point. Okay, in this region there is no equilibrium point. Then in that case what happens, that if you take any solution, okay, so see, the orbit is nothing but the solution, the phase portrait or the trajectory of the solution in the plane. Okay, so what it says, that any solution you choose, okay, it will converge, okay, it will converge to some simple closed curve. So let me, so the first thing is that it guarantees you that, okay, some simple closed curve is there. Now simple closed curve means that it is a periodic solution, right? This is what we have seen in the maybe last lecture, last session, I think. So this closed curve is, it's closed, that means the solution is periodic. Okay, so it says that there will, so what it says, in other words, like it says that there will exist a closed curve. Okay, and any solution or any orbit of the system will converge to, okay, to this one. So maybe either it will converge or diverge, I mean, it depends. Okay, so it's like the, it should be spiraling around that curve. So this theorem guarantees you existence of this closed curve or closed orbit or periodic solution. And the furthermore, it says that if you take any other orbit, it will be spiraling around that curve, closed curve. Okay, spiraling around that closed curve, that's all we can say. Okay, okay, so this is what this theorem says. So using this theorem you can say whether the periodic solution exists or not. That kind of question you can address. Okay, so there is one other notion, it's called limit cycle. Okay, so if you take any closed curve, okay, then that closed curve is a limit cycle or not. And what does it mean? So the limit cycle is like, if the orbits, so this is a closed curve that we have, this closed curve is called a cycle, I mean this one. So suppose this is a, I mean just in R2, suppose this is a closed curve that you have, and closed curve by I mean the solution, it's a closed orbit. Okay, so this is coming as a solution, so xt comma yt. Okay, so this will be called a limit cycle of this system. Okay, if the orbits of the system spiral into it. So if you take any other orbit, orbit means any other solution, if you choose, the trajectory will either converge to this one or it will diverge. So maybe the arrow can be like this or this. Okay, so either as t goes to infinity it goes to that curve, okay, or as t goes to minus infinity it goes to that curve. So this kind of thing. Okay, so that's why this limit, this name limit comes because of this thing. that it is a limiting case. So as t goes to infinity or t goes to minus infinity, we say that if this orbit spirals in that, then we say it is a limit cycle. So the name limit comes from this limiting behavior. And in other words, what you can say, so this was one thing. So this is one definition, or the simplest definition is like, suppose this is a curve. So this will be called a limit cycle of this system if it is a isolated limit cycle, okay, or isolated closed trajectory. I mean, not limit cycle, it is a limit cycle if it is a isolated closed orbit. Okay, what does it mean? It means that if you take any neighborhood, so if you take any neighborhood around this closed trajectory, okay, there exists no other closed curve or closed cycle. I mean, right? So if you take any, I mean, solution or any orbit in this region, okay, it will be not a cycle, it will not be a closed curve, right? And I mean, these two are equivalent in the sense that, you see, this line is telling you that if you take any orbit, it will go to converge to this one. So it is not periodic, it is converging to this closed orbit. That means it cannot be a closed curve, right? Because as t goes to infinity, it is going to this curve. Okay, so in a neighborhood there is no closed orbit at all. So that means these two definitions are equivalent. Okay, so these are the two ways of saying the same thing. Okay, so this is what the limit cycle means, and this limit cycle will be called stable if you remove this point. That means it will spiral into that as t goes to infinity. Okay, so pictorially it's like, if you have this closed orbit, there should exist a neighborhood. It's similar to what we have said about the stable equilibrium point. Okay, so if you have this neighborhood, then if you start with any solution here, then it will spiral around this black curve. Okay, so there should exist a neighborhood such that whatever point you choose as the initial data, it will spiral around this black curve. Okay, and if this spiraling is going as t goes to minus infinity, then it is unstable. Okay, so if the arrow is like this, we say that it is stable. Okay, and if the arrow is reversed, okay, so starting from here, if you are going away from this one, then it's called unstable, like the usual notion what we have of stability and instability. Okay, okay, so this is what it is about this limit cycle. Okay, okay, so now let us look at this problem. So you have been given this system which is a nonlinear system, and here the question is to find the okay, so there is a typo. So find the domain where the problem has limit cycle. Okay, so limit cycle, at first what we need to make sure that it is a closed curve. That is the first thing, that periodic cycle. Okay, that it should be a periodic curve, right? And it should be isolated. So limit cycle means that you have to look for the periodic solution, and the second thing what we want to make sure that the closed curve, so this is periodic solution or closed curve, right? The second thing is that the closed curve should be isolated. That's all we want to make sure. And in fact, this is guaranteed by this Poincare Bendiction theorem, right? This is what it says, that if you choose any solution which is bounded, then this is the conclusion says that its orbit must spiral into the simple closed curve, right? Which this definition is telling you, right? And this closed curve itself is a, so this is the first line is about that the simple closed curve is isolated, and the second line is saying that this closed curve itself a orbit. So a closed orbit exists, and any solution, okay, spiral in that closed curve. So this theorem actually guarantees you the existence of closed curve, sorry, isolated limit cycle. So what we need to check is this assumption. So we just need to verify this assumption that if you get a solution which is bounded in a region, that's good enough. That will guarantee the existence of limit cycle. Okay. So see what this theorem says, that you have to look at the solution xt, yt, which remains bounded in some region. So that region we have to find, and the solution also, like where it is bounded. That's it. Okay. So looking at this problem, so this is, let me rewrite this system. So x prime is y plus x 20 minus x square minus y square, and y prime is minus x plus y 20 minus x square minus y square. Okay. So this is the given system that you have in hand. Again, let us multiply this one by x and this one by y. So x prime plus y prime is equal to, so this will cancel out these two. Okay, and then you have x square 20 minus x square minus y square plus y square 20 minus x square minus y square. So this means 1 by 2 d dt this is equal to x square t plus y square t 20 minus x square t. Okay, so or maybe let's take 2 here. Okay, so this is what we have. Okay, now if you look at this expression, this d dt is like, what does d dt, this represents how the distance of solution xt comma yt changes with respect to time. Okay, this is what it tells you, right? So if you look at this right hand side, you see this is always greater than equal to 0. Okay, the second one tells you that this will be greater than 0 if x square plus y square is less than 20, right? And it would be negative if x square plus y square is greater than 20, right? So what we can tell using this, I mean this conclusion, I mean this observation, is the following, that the solution that, or let me write the solution, or just the value of x square and y square, okay, or along the solution. Okay, so that x square plus y square, this increases, right? This is what d dt. So when it is positive, it is increasing with respect to time. So it increases the radius. So I should write x square t maybe, or okay, let it be. So the radius of the solution so increases along the solution. So along the solution, the radius increases when x square plus y square is this less than 20. Okay, and decreases when x square plus y square is greater than 20, right? In other words, I mean in terms of picture, it's like maybe like this. So let me draw this. So this, you just remove this 0 equilibrium point. Okay, and let me say this is the circle of radius 20. Okay, what it says that, so let me say this is 20, this unit is 20. Okay, so what it says, that if your x square plus y square is less than 20, that means suppose your solution at, I mean, the sum point, the solution is at this, in this inside this circle. Okay, then it says that this x square plus y square will increase, the distance will increase. So suppose this is here, it says that the distance x square plus y square will keep on increasing. Okay, and the other thing what it is being said, that if your initial data or some data at some time, if it is here, then it says that when your x square plus y square is greater than 20, then the radius will decrease. That means it will be, sorry, this will keep on, this will keep on decreasing. Okay, this kind of behavior you will see. Okay, so this is what this line means. Okay, nothing special. Okay, so this kind of behavior of the solution we have. Okay, so we had to find that, where is it, you had to say that you have to find a region, you know, that how the solution is behaving, right? So if you consider this black circle, so I mean this black disk, if you color this one, if you consider this colored region, okay, I mean except the origin, then in this region you know that the solution is bounded in this region. So you can clearly see from the behavior that it cannot cross this black circle, because if it crosses again it will push it towards here, right? So this will remain bounded in this black shaded region. Okay, so you have this much. Okay, so I mean the ideal region should be this, the circle or the disk. Okay, so that's why, so you just maybe let us denote this r by xy such that x square plus y square is less than or equal to 20, this black shaded region. But so this is the first thing, that it should be bounded in that region. So we consider one region, we found that. Now the second thing what we need to make sure, that that region should not contain any equilibrium point, right? So it should not have any equilibrium point. Okay, so now let us look at what the equilibrium point this system has. So equilibrium point means this should be zero, both the things, right? So for equilibrium point, let us look at this function. So you have y plus x 20 minus x square minus y square equal to 0, and the second one is minus x plus y 20 minus x square minus y square. So from here what you can conclude is y is minus x 20 minus x square minus y square. And now using one you can say, so here from here you can conclude x is y 20 minus x square minus y square. Okay, so now if I use 1 here, so I'll get minus x 20 minus x square minus y square. Okay, and from here I can cancel this x, so this will be 1 equal to minus, write in 20 minus x square minus y square equal to minus 1. So this is possible when if x is non-zero. Okay, and if x is 0 you can clearly see y is 0, so that 0 0 equilibrium point is there. So we are anyway in this. Okay, I think I did not mention, so let us make this as 0 greater than this, so that in this region like 0 0 is not an equilibrium point. Okay, so it is strictly greater than 0. So in this region 0 0 is not, so we can ignore that equilibrium point. We are looking for non-zero equilibrium point. Okay, so here this is the case. So this means x square plus y square, just a second, so this would be 21, is it? Everything fine. Y is minus x. Okay, if this is the case then we don't need to worry about it. 1. Is it? I don't know. This calculation is correct, right? 20 minus x square is equal to 1. Something looks equal to, yeah, it looks fine. So this x square plus y square is 21. That means the circle, I mean the bigger one, is the set of equilibrium points, right? So this one here only, let me substitute. So maybe this circle, okay, so this length is, let's say, 21. So this circle contains the equilibrium point. Okay, all the points on this line, on this circle, is an equilibrium point, right? So this region does not contain any equilibrium point at all. That means from this theorem we have found one bounded region, that is this R, what we have defined, that's x square plus y square greater than 0 and less than equal to 20. In that region we know that there is no equilibrium point, and so this theorem guarantees us that it will contain one closed orbit, and any orbit will converge to that closed orbit, right? This is what this theorem guarantees us. So this, so yes, so the conclusion would be, so R contains no equilibrium point, so maybe contains no equilibrium point, hence now what can we say, that the system has a limit cycle in the region R. Okay, and this is just following from the Poincare-Bendiction theorem. Okay, so this is by Poincare-Bendiction theorem. Okay. Okay. So we just had to find a region, and we have to just look at whether there is some equilibrium point or not in that region. Okay. In our case, we were lucky. In case, suppose that if you got some equilibrium point which is lying inside this region, so let me just explain. So suppose this was your region, what you started off with, where the solution remains bounded. Now suppose that the equilibrium point is some point lying here, okay, or no, maybe not closed curve, but let's say these are the equilibrium points which is lying in this region. So in that case, what you can do is you can consider this, consider any bigger circle over here, okay, and then you consider this region, okay, but here will have to guarantee that the solution remains in this region, okay. So here the solution should be bounded. Now I mean, what I mean is, let's suppose this is your R, new R, but here you have to make sure that the solution remains inside this R, right? In this bounded region only the solution should stay. So if you can make sure that, then everything's fine. Okay. Okay. Okay, now let us move to another theorem, which is called Bendixtion's non-existence theorem. And non-existence, we'll see from the theorem why it is called non-existence. So here you see, in this theorem we guaranteed the existence of closed orbit. Okay, that means a periodic solution, right? Here it will tell you when it will have no periodic solution. Okay. Okay, so suppose you have a domain D, and so this is the system under consideration. So what you do, you just look at this derivative. So when you are dealing with x prime, just take the fx. When you are when y prime is equal to gy, you have to take the yth derivative of g. Okay, so I mean the relation is like this. So y prime gy. Okay, this is just to remember. I mean the system can be like y1 y2 f g like this one, so you will have to f y1 plus g y2. I mean, this kind of thing. This is what it means. Okay. So you have to look at the sign of this term, this function. So take the partial derivative of f and g with respect to x and y respectively, and check the sign of this function. If it has same sign throughout this domain D, what you are considering, then it will have no solution, periodic solution in that domain. Okay, so if you have some domain, and if you know that fx plus gy is either positive or negative in this region, then you can say that it will have no periodic solution in this region. Maybe here it can have, outside D it can have periodic solution, but in this region we can say that there is no periodic solution. Okay. Okay. So that's all about this theorem. So the earlier theorem was guaranteeing you a periodic solution. Here we are looking for the non-periodic solution. Okay. Okay. And this type of problem actually you can address in two ways. Okay. I'll tell you. So let us consider this system. Okay. Here it's a second order differential equation, but you can always convert it into first order. Okay. So let me just write the, so suppose this x is equal to z and y is equal to z prime, which is x. So y equal to x prime, then y prime you can write x double prime, which is z double prime, and z double prime is minus z4 or 1 minus z4 z prime, and then minus z, which is nothing but 1 minus z4 is 1 minus x raised to the power 4. Z prime would be this one, which is y, and then minus x. Right, so this is the conversion. Okay, so I mean, overall the system can be written as this. So x y prime is equal to, so x prime is nothing but y, and y prime is minus x plus 1 minus x4 y. So this is the non-linear term that we have. Okay. So let us first use this theorem. That would be much simpler. Okay. So here you see this is your f. So this is f comma g. Okay. So let me say this is the first method what we just saw. So if you say this is fx plus gy, if you do, then what you get is the fx is 0 and gy is 1 minus x4, right? So this is your this derivative. Now your question is saying that show that the system this has no non-trivial periodic solution in this one. Okay, so the domain is given to you. So now what you have to check, if the sign is preserved in this domain, then we are done, right? Then we can say that it does not have any periodic solution, correct? So you can clearly see that for D, which is given as x comma y in R2 with x belonging to minus 1 comma 1. Okay, in this domain you can see that this fx plus gy, what is the sign of this? This is always less than 1, so you have this greater than sign, right, in this domain. So you have one sign in this domain. So by Benedict's non-existence theorem, the system has no periodic solution in the domain D. Okay, so this is much simpler. I mean, this is a much simpler trick to check whether the system has a periodic solution or not. I mean, if the domain is given to you, right? Okay. Now I was talking about the second one. So actually in some cases just looking at the stability of the system you can guarantee something. Okay, so let us explore that. So let me recall this system. So let me just copy this one. Okay, now the linearized system would be system is this x y prime equal to 0 1 minus 1 0 xy, right? This is the linearized system, and the eigenvalues of this one value is plus minus iota, right? This is the eigenvalues that we have for this system. Yeah, I hope I'm correct. Yeah. Okay, then from this one what you can conclude, oh sorry, here, sorry, I mean, okay, so here I think you see this is also the linear part, I mean this one. So plus y is also there, so here it will be 1. So the eigenvalue would be, sorry, so this, suppose this is a, so if I calculate a minus lambda I equal to 0, then that would be minus lambda 1 minus 1 1 minus lambda equal to 0. So this means lambda, sorry, lambda minus 1 plus 1 equal to 0. So from here we can say lambda is 1 plus minus 1 minus 4 by 2 root 3 iota by 2. Oh sorry, minus 1 plus. Okay, so this is the eigenvalue what we got, right? So let me just rub this off, or maybe write it here. Okay, so the eigenvalues what we got is this kind of, so complex eigenvalues, and with the real part greater than 0. So from here what we can say, so maybe let me go to the next page. Okay, so 0 0 is an unstable equilibrium point for the linear. Now in this case we can conclude for the non-linear system as well. So for the linear and non-linear system, right? In fact it is a spiral, right, from here. So maybe let me mention that also, unstable spiral for the linear and non-linear system, right? What does it mean, right? So it is going away from origin and it is spiral. I mean, this is the most important point what you can look at. So spiral means it is always, it cannot be closed, right? Yeah, so what it says that, suppose this, about this zero equilibrium point we are talking, right? So if you consider this some epsilon neighborhood, so okay, so one disadvantage would be that you cannot guarantee in this domain, I mean the domain what was given to you minus 1 comma 1, but actually you can say in some smaller neighborhood, in fact you can say in, sorry, you can say in any neighborhood. So let me explain you by this. So first recall the definition of stability, stable equilibrium point. Okay, so what does stable means? Stable means that if you have some epsilon ball, okay, then for this epsilon there will exist a delta, okay, so that if you choose any initial data from here, the solution will remain in this orange box, right? It will remain inside this orange thing. But when you say, so let me write here in the mathematical terms, for epsilon greater than 0 there exists delta greater than 0 such that something happens. Okay, okay. mm, okay, so yeah, so you cannot actually conclude, but okay, let me mention what I want to say. So it is unstable. I mean, the equilibrium point 0, 0 is unstable. That means there exists some epsilon neighborhood. Okay, the negation of this, that there exists epsilon greater than 0, some epsilon naught, such that for all delta greater than 0, the solution moves away from this epsilon, right? So that means, for suppose you get some epsilon naught such that whatever delta you choose, delta means the ball where you can choose the initial data. So any delta you choose, the initial data, so whatever initial data you choose in some sense, right, the solution will never stay in this epsilon neighborhood. Okay, so it will always go away from this, right? This is what this says, and goes in the spiral way, right? So it would be like this if the solution starts from here, I mean, or in from any point actually. So it will never stay in a ball of any, I mean, of some epsilon naught. Maybe it can stay, so by the, I mean, it can stay in some other epsilon ball, but there exists one epsilon naught where it does not stay, the solution will not stay. Okay, and it is going in a spiral way. I mean, this is the most important thing what you can say, that it is spiral. So if you start with some initial data, it will, I mean, go in a spiral fashion. So it can never be closed curve. That means there cannot be any periodic solution. Is this clear? Karthike, I think you were asking something like this, right? I mean, this is the argument what I gave you in the last week. I mean, this argument,
Mm.
right? But now since you have studied this one, you can
Yes.
use this also.
Yes.
Okay. Okay. So, so this is all about, I mean, about this one. So,
One doubt, shall I?
yeah, sure, sure.
In this previous example, right, we you told that that x square plus y square 20.
In this example, you are saying?
Yeah,
Mhm.
that 0, 0 is also one of the equilibrium points.
Correct,
in
correct.
this case.
Huh.
So if you want, as per definition, there should be some bounded region, right?
Correct.
So here, where that region comes, whether we have to see near to 0, 0, you have to make a ball, and where that boundedness is coming.
No, this is a bounded region, right? So let me draw it here. So it's like, this is, you exclude this point, so it's like this, right? And then you take this ball. So this shaded region is a bounded region. I mean, I'm not talking about the closed. So it's just bounded.
Okay, that means we should exclude that 0, 0. Then above that and below this is the bounded region.
Yeah, so this is what R is, right? So this is greater than 0.
Okay.
Yeah. So we just have to look around a bounded set, and we know, in fact, that if we choose any data which is non-zero, right, the solution remains in this black shaded region, right? So we have this bounded region where the solution stays in it. Okay. Okay, so we talked about this problem. Okay, so you can clearly see that this is a very easy criteria to check. Sorry, not this one, this one. Okay. Now let us talk about the Lyapunov stability. So this is on a, using a functional, we can determine whether the system is stable, asymptotic stable, or unstable. Okay, so this is, we have to find, so the whole idea is that you have to find a function, a scalar function, that means the v. So suppose you are in, let me, so suppose you, this is your system in Rn, so this function f is from Rn to Rn. Okay, so it's a vector. And this v you have to, okay, so let me first give some definitions. So suppose this v is a function which is in this Rn to R, this is a real valued function. Okay, and this is said to be positive definite if this vx is greater than 0 at all points other than 0, and at 0 it is a 0. So v at origin is giving real value 0. So this 0 and this 0 are different. So this is a vector and this is a real number. So this belongs to R. Okay. So v at 0 should be 0 and it should be strictly positive at other points. So this is the positive definition of positive definite functions. Okay. And negative definite is like minus v should be positive definite. Okay. So v at 0 should be 0 and v should be negative at other points. That's it. Okay. So these are few definitions. Okay. So let me just give you a main idea what we are doing. So see, we have been given a system. This is a system that we have in our hand. Okay. Now we have to talk about so suppose 0, 0 is an equilibrium point. Okay. And now we want to talk about whether the equilibrium point is a stable, asymptotic stable or unstable. Okay. So there is a way. So what you have to do, you just try to find a function v, okay, from omega Rn to R, which is positive definite. Okay. So this is the first thing that you have to make sure. So try to find a function v which is a positive definite. Okay. Now using some condition on this d dt of v. Okay. So let me say this one. So see, this v is a function from Rn to R. This is just a function. Now what we do, look at this one. So v at yt. Now see, this yt is a vector in Rn, right? For each t. So now we'll look at about this function along the solution. So suppose this is a solution yt. Okay. So now we are looking at the value of v along this curve. Okay. So that's what v yt means. Okay. Now what you do, you have to look at the derivative of this function. Okay. d dt of v yt. So depending on what, we'll see some condition. So depending on this function, so d dt v yt is again a function, right? Now looking at the signs or what kind of function it is, we can conclude whether the point 0, 0 is a stable point or asymptotic stable point or unstable point. Okay. Now, okay, so let us now look at that criteria what we have. The other thing is that, so we'll see what the criteria are, but suppose, there could be cases that you find some function v and I found some other function v tilde, okay, which are positive definite. And if I look at this condition, whatever condition we'll see in each of the cases, so whatever v we choose, the suppose 0, 0 is asymptotic stable, okay, then this property will be conserved. It is not something like if you change v, this will change, okay, and that should not even happen. With this v you have to find. Now looking at this function d dt of v yt, you guarantee that whether it's depending mainly on the sign, what sign it carries and what sign it has, we'll say that whether the point is asymptotic stable or not, or some other stable or unstable. But even if I change this function v to some other v tilde, if I find some other v tilde, but again this property will be preserved. Okay. So v could vary, you can have different v, but the property will be preserved. So if the point is asymptotic stable, then the properties for each of the v will be same, even if for stable or unstable, the property is not going to change. Okay. Okay. So now let us look at what kind of condition we have. Okay. So for stable, okay, so first let me mention what this d dt of v yt is. So suppose this v, that is a function from Rn to R, and d dt, if you want to look at v of yt, so this is nothing, using chain rule if you use, so v is a function from Rn to R, so the derivative of v would be the grad v, right, for this function Rn, and then y prime of t. So this dot product. Now y prime t, that this is y prime t is f of y. Okay. So this is del v dot f. So this is like this d dt of v is nothing but the gradient of v times the dot product with the function f. I mean this vector what you have been given here. Okay, so you have to look at the sign of this quantity. Okay, so this is what ddt is. Now let us come to the theorems. Okay. Okay. So suppose you find some vy which is positively definite. So this is same for each of the statements. I mean vy, the functional v, this is called Lyapunov functional. Okay, I mean you gave this name. So the function v should be positively definite. This is the first criteria, and this is in fact for each of the one. I mean whether you deal with stability, asymptotic stability, or instability. Okay, so okay, let us talk about this stability. So suppose there is a scalar function vy which is positive definite. Okay, and for which this derivative or the dot product grad v dot f is less than equal to 0. Okay, on some region omega. So you are talking about a stability around this point origin, right? So we are talking about whether this 0 0 point is stable or not. So I mean in I mean we have the notion that we, I think I have not mentioned it, but here you can assume that f of 0 is 0. I mean 0 is the equilibrium point. Okay. Okay, and we will be, I mean we'll just stick to some neighborhood of that 0. So omega is some neighborhood of 0. Okay, then if you have this property of this derivative of this on some region omega which is around this origin, then we say that the equilibrium point 0 0 is stable. Okay, and I mean for asymptotic stability you need one more thing. So you know asymptotic stability means it is stable with some other asymptotic behavior of the solution, right? This is what the definition is. So when we talk about asymptotic stability, we say that this sign should not be just less than equal to 0, but it should be strictly less than 0 except the point 0. Okay, so at equilibrium point this can be 0, I mean, but other than 0 this has to be strictly less than 0. Okay, so this is, so negative definite is what I have defined just now. And okay, so here you just consider around some ball, but this ball and omega you can even you can change it for omega, it doesn't matter. Omega in particular is a ball, that's it. So this has to be negative definite. So negative definite means it should be strictly less than 0. Okay, at 0 it can be 0, but other, I mean at 0 it has to be 0, but other than 0 it is strictly less than 0. Okay, so if you have this condition, then the point 0 0 is called asymptotic stable. Okay, for instability, so suppose you have a scalar function v. Okay, so in all this theorem you have to find v. If you can find v, then you can say something v with these kind of condition. Okay, so here instability means if there exists a scalar function v, so with this condition obviously, okay, such that this function, so earlier we said that this has to be less than equal to 0 or strictly less than 0 depending on the point is stable or asymptotic stable. But here what it says that whatever be, whether it is strictly positive or negative, we don't care. Okay, whatever sign it has, but main thing is that around the point, so around some neighborhood of 0 0, okay, there should exist a point y naught such that whatever sign it carries, so suppose d dt of vyt is positive, and if you can find some point y naught where it is positive, then you are gone. I mean the point is not stable. So here we have not put any condition on v. So earlier we had this v has to be positive definite, but here we don't have any condition on v. So if this derivative has positive sign and you can find a y naught around, I mean in some neighborhood of 0 with this property, then it is unstable. And if this has negative sign and you can find some point y naught where it is negative, then also, so the sign of this and this should not match, okay, for instability. Okay, now we'll see some examples. and from that I think it would be much more clear. Okay, so this is what the theorem is. So for guaranteeing the stability, whether it is stable, unstable, or asymptotic stable, we can use this theorem. So the main task is to find v. Okay, so depending on problem it will change. Okay, so let us look at this example. So you have been given this three systems. Okay, and you can clearly check, like in each of these three systems, 0 0 is an equilibrium point, right? Okay, so now we have to check about the stability of this equilibrium point. Okay, so in all these examples, so let me begin with general thing, then we'll come to particular each of the problem. And okay, so let me first define this v is a function from r2 to r and given by, so here we are dealing y1 y2, so v of y1 comma y2 is y1 square plus y2 square. Okay, so this is the functional what I am considering. You can clearly see that this v is positive definite. Okay, the second thing what you can check is that the grad v is 2 y1 y2, right? This simple. Okay, so this is the general thing what we have got. Okay, now let us look at each of the problem one by one. So let us consider this one. So let me write this as y prime is, so this is minus y1 cube minus y1 y2 square. So here I'll have y, sorry, here it will be y2. Here I'll have y1 minus y2 cube minus y2 y1 square. See, this is the system that we have in our hand. Okay. Okay, so this is the system. Now this is your fy, right? So this is your fy. Okay. Now let us check. So d dt. So for stability or asymptotic stability, we just need to check the derivative. So d dt of vyt, if I do, so this is nothing but grad v times f, right? So that is 2 times y1 y2 dot product with minus y2 minus y1 cube minus y1 y2 square, y1 minus y2 cube okay. Now if I take the dot product, what I get is, so you see this y1 times minus y2 and this y2 times y1 will cancel out, right? So this will be gone. So the rest of the terms is minus y1 4, okay, and then you have minus y1 square y2 square plus, like this, plus you have from here you have, sorry, minus y2 raised to the power 4, and then you have y2 square y1 square. So this is just 2 times this. So this is nothing but this is minus 2 times y1 square plus y2 square whole raised to the power square, right? So this is what we got. So this derivative is given, I mean, is given by this expression. Now you can clearly see this expression is strictly less than 0 for y1 y2 not equal to 0, right? So this d dt of vyt is strictly less than 0. Shit, is just, so I'll just write is negative definite. That is the simplest thing. Okay, and hence what you can conclude, when the this derivative is negative definite, then you, from here what you can conclude, that 0 0 is asymptotic stable. Okay, so this is for the case 1. Now for the second case, so the system is, okay, so just you have to put plus sign here, and so instead of minus you will have plus. So maybe you can copy from here. Okay, so here you will have plus 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 plus, right? Again, if we do the same thing, if we try to find d dt of vyt, okay, so what we get from here is, so 2 times, again I'll do the grad v y1 y2 times this whole function, right? And now if I calculate this dot product, what I get is 2 times, so this y1 y2 again will cancel out, and I'll have everything will be in plus, so I can directly write this would be y1 square plus y2 square whole raised to the power square. So this is what we get, right? I mean, so from here we can clearly see that this functional is not appropriate for stability or asymptotic stability, because for those things we know that this should be less than equal to 0, but here we know that this is greater than equal to 0. So let us check whether this functional is suitable for instability or not. So I mean, from so what I'm saying, so looking at this, the functional v, the function v is not suitable for checking stability or asymptotic stability. Okay, I mean, but now let us check whether this functional can be helpful for guaranteeing instability. Okay, so that is our task. So for the instability, what we need to make sure that if there exists some point where the sign, so here you see that the sign is greater than equal to 0. In fact, this is positive definite. So what I can say, this is positive definite. Okay, now if you can find some point y naught where this is again positive, so we know that this is greater than 0. Okay, and we know that any point you choose v of y naught, if y naught is non-zero, we know that this is greater than 0, right? This is how we define the functional v, right? The v is also positive definite. So since the sign matches, what we can say, and so the equilibrium point 0 0 is unstable. Right, this is what we can say about this one. Okay, so this function is not suitable for checking asymptotic stability or stability, but this works well for the instability. Okay, and in fact you can, if you can choose any function v, but it cannot be, I mean, you cannot get this kind of, you cannot be sure about this, I mean, you can never get this thing. Okay, so it's not very particular about this function. You can try with other function, maybe you can raise to the power 4 or something, whatever you want to do. Just make sure this condition for checking the stability or asymptotic stability, but whatever v you choose, if it satisfies the proper condition, you can say that for another v cannot be asymptotic stable, otherwise this theory would not be meaningful at all. Okay, so just don't think that this is a particular choice of v what I have made. You can choose other functional as well. Okay, and you can draw conclusions. Okay, let us look at the c part. Okay, so the c part is y prime is equal to, so again the linear part is same. Okay, so this is also, I mean, something that I missed to say. So you see, in all these three cases the linear part is same. So if you do the linearization around 0 0, you'll get the same system. Okay, and you know that the if you, the eigenvalues would be plus minus I, so the linear system is stable, so the real part is 0, so you cannot conclude about non-linear thing, right? From the theorem what we have studied, when real part is 0, we cannot conclude any conclusion about the stability of the equilibrium point for the non-linear system, right? So using this functional, Lyapunov functional, we can conclude. Okay, so that is one thing to be noted here, that the linearized system is same in all the three cases. But we have seen for the first two cases that okay, in this case it was asymptotic stable, but in this case it is unstable, the equilibrium point 0 0. So we could not conclude from the linear system, right? Okay. So let us look at the third C part. So you have minus y2 minus y1 y2, and here you have y1 plus y1 square. Okay, so this is the system what we have. Okay. Now here again, if we look at the derivative, so d dt of v yt, this is grad v is 2 y1 y2, and this is minus y2 minus y1 y2 y1 plus, is it y1 square? Okay, y1 square. So you have y1 square. Okay, so now if you do the dot product, you see y1 minus y2, so minus y1 y2, and here you get y1 y2, so it is cancelling out. And here you see minus y1 square y2, so this 2 multiply to get minus y1 square y2, and here you get plus y1 square y2. So the derivative, I mean the dot product is 0, right? So this is, you can say that this is less than equal to 0, right? And the functional v is positive definite. So what you can say, so the equilibrium point 0 0 is stable, right? So you see that in all the three cases, because of different non-linearities, we got different property of the equilibrium point 0 0. Although the linear system has the same property, that the equilibrium point 0 0 is a center and it's a stable point, right? Okay. Okay, so this was about this example. So you can check this example as well. So in this system, the proper functional what can be chosen is, so consider this functional v y1 y2 y3 as y1 square y2 square plus y3 square. Okay, and now you do the same analysis. So this grad v, you just calculate this one, so you'll get 2 y1 y2 y3, and here this function f y or f y1 y2 y3 is given by, so what is this function? This is, okay, here we are in x, so let me write in x, x1 x2 x3. So f is minus x2 minus x1 x2 square, and then plus x3 square, and then minus x1 cube, x1 plus x3 cube minus x2 cube minus x1 x3 minus x2 x3 square minus x3 raised to the power 5. So if you do this dot product, what you get is 2, so you multiply with x1 the whole thing, so minus x1 x2 minus x1 square x2 square plus x1 x3 square minus x1 raised to the power 4. With x2 if you do, you'll get plus x1 x2 plus x2 x3 cube minus x2 4, then you have minus x1 x3 square minus x3 square x1 square minus x2 x3 cube minus x3 raised to the power 6, right? So you can clearly see that this cancels with this, and then let's see x1 x3, so this cancels with this. What else is remaining? So this is another problematic term, so this cancels with this. Okay, now rest is fine. Okay, so what we got is 2, you have, so let me take minus common, so you'll have minus 2, and then you have x1 raised to the power 4, then you have x2 raised to the power 4, and then you have x3 raised to the power 6, and then you have cross product minus x1 square x2 square, sorry, with plus, and then you have x1 square x3 square, right? So you see this is clearly less than equal to 0. Okay, and in fact this is 0 only if all the things are 0, because all things are non-negative. So you can say, so I mean, so what can be said is, so d dt of vy is less than 0 for y1 y2 y3 belonging to R3 minus 0, and okay, it is, so that's enough, and at 0 it is anyway going to 0, so this 0 0 sorry 0 0 0 is asymptotic stable. Okay, so this was for this problem. So here we got that the origin is asymptotic stable. Okay, now I mean, there are few particular type of functional that we can conclude. I mean, we can find Lyapunov function in a particular fashion. So I mean, these are few construction that is already in the lecture, but I have written it here, so I'll skip this. I mean, the things are quite simpler, so I'll just give an overview. So suppose you have this kind of nonlinear system. Okay, so you have this condition. Obviously this is required for the 0 to be equilibrium point, and this is tells you that 0 is an isolated equilibrium point. Okay, and you have this function is differentiable, so that you can guarantee the existence of solution, existence and uniqueness by Picard's theorem. Okay, so this is just to make sure everything works in a good I mean, everything is in a perfect setup. Okay, then you can give the Lyapunov functional as this one. Okay, so in all the earlier cases you can try with this kind of functional, and you can see, I mean, this is one of the obvious where you don't need to use any kind of manipulation. Just look at this kind of functional. Okay, this v, and but all this construction, let me tell you, all this construction whatever is mentioned is mainly for when you want to check about the asymptotic stability. Okay, that's it. So if you consider this kind of functional, okay, and when you consider this type of functional, the derivative will be given in this form. Okay, so see, this is just the Jacobian matrix. Okay, so to check, so what you can, in conclusion, what you can say, that looking at the asymptotic stability, you just, I mean, that means looking at the sign of this, you just need to look at the sign of this. I mean, whether it is negative definite, or I mean, it can be equal to 0 also at some point. Okay, so if this matrix, the transpose of the Jacobian plus the Jacobian, if this matrix is negative definite, okay, in some, I mean, epsilon neighborhood of 0 origin, then you can say that the solution is asymptotic stable. Okay, so if you have this kind of system, you can just look at df plus df transpose. If this matrix what you get is negative definite, okay, then you can say that the origin is asymptotic stable, and the underlying functional, the Lyapunov functional, is this one. Okay, so if you have a feeling that okay, 0 0 is asymptotic stable, just look at this matrix. Okay, if you can conclude that this matrix is negative definite, then you are done. Okay, so this is one of the easy method. Okay, and in that case, if you someone is asking what the functional you chose, just give this functional, so which is the transpose of this times this f vector. Okay, so this is one of the method. Let me just keep it here. Okay, the other one is that for the linear system, that if you have a linear system like this, okay, then you can give under certain, I mean, special cases, that when the matrix what you are considering here has distinct eigenvalues, so all the eigenvalues of this matrix is distinct, that means diagonalizable kind of thing, then in that case you can say, uh, so you construct this B matrix, and this is the Lyapunov functional. Okay, using this Lyapunov functional you can conclude that the system is asymptotic stable. So if a matrix A is given to you with distinct eigenvalues, okay, then you can directly say that this is going to be asymptotic stable. Okay, I think this, okay, I mean they this is the I mean just these things, all of the things just has been written in a sense so that I can write this matrix. I mean, this is nothing, it is just a way of writing. I mean, just this line has been just written to write this matrix P. Okay, so if you arrange your eigenvalues in this fashion, then you can write the Lyapunov functional in this way, where the matrix B is given in this way. Okay, and in that case you will get the solution, zero solution is asymptotic stable. Okay, but I mean, sorry, you can actually in this case you can make sure that this, so D is the diagonal matrix. Okay, not diagonal matrix. When you have complex eigenvalue you will not get a diagonal matrix at all, but I mean, you know that if alpha plus minus iota beta is the eigenvalue, the corresponding matrix is like this: alpha beta minus beta alpha, this kind of thing. So that matrix D, I don't know where I have written it. Okay, I have not mentioned it, but D is something that you reduce it in some simpler form, dz, where D is the canonical form. That's all I can say, that D is the canonical form of the matrix A. Okay, so that is the matrix D. So you can check that this will be -1 if you choose B to be in this fashion. Okay, then, I mean, that's just okay, and then you can, so here it is function. So then there's another, this is the general thing what we generally chooses, that just consider the function, energy function of the system, underlying system. Okay, so this is what we have done in the earlier examples. Okay, so do you have any doubts? I mean, this was it for today, so if you have question you can ask. And for the previous examples, wherever I have talked about asymptotic stability, you just check this condition. Okay, this condition, just to be comfortable with this thing. You can say that this matrix whatever you compute in the previous cases will turn out to be negative definite. Okay, okay, if you have any question you can ask, otherwise we can stop here. Okay, if there's no question, let's stop here. See you next week. Okay.